So really what I wanted to do was focus on exploitation and look at it in the context, specifically of FreeRTOS with lightweight IP, which is a TCP/IP stack implementation. And people have been doing research like this for well over a decade, and this is just really a small list of some of the relevant work. Most recently, Yannick Formaggio looked at VxWorks and found vulnerabilities, and that's some really awesome recent research, but a lot of the stuff I have here goes back over 10 years. And yeah, this is another contribution to the space. To give you an outline of what I'll be talking about for the rest of the talk, we'll talk a little bit about bug hunting. We'll look at internals of FreeRTOS and lightweight IP and get some context. We'll talk about stack smashing in practice and also talk about some other bug classes. And then I'll go through an example of end-to-end exploitation. So let's talk about bug hunting. When you look at IoT devices, authorization issues are common. Vendors are baking backdoors into these systems. Those are all, the kind of bugs you think of when you think of devices in this space. But that wasn't the focus for the research. I was restricting my focus to memory corruption only. And as I mentioned, developers, everything from the OS to the applications that are being hosted on the OS are going to be written in C. So we're really expecting the usual suspects in terms of bug classes, buffer overflows, heap corruption, and so on. And in my case, I started by auditing whatever I could get my hands on. Like I said, there's a lot of software out there. So looking at FreeRTOS, lightweight IP, in particular, Expressifs, their RTOS SDK, which is based on FreeRTOS. Lots of contributed servers for lightweight IP on GitHub, file system implementations like FATFS, constrained application protocol implementations, multicast DNS, and so on. I mean, if you look around, it's not hard to find things to look at. Bugs were found via code review as well as fuzzing, and honestly, some of the most serious bugs, I found them just because I decided to look. They weren't hard to spot at all. I should mention there's lots of places where I didn't find bugs. A lot of the code is quite good. FreeRTOS and lightweight IP, they've been in development for a long time. I didn't find any issues. I did find a lot of bugs in, like I said, contributed servers, SDKs, and in particular, Expressifs, Internet of Things platform based on FreeRTOS. And so far, I've disclosed something like 19 vulnerabilities, and they've been fixed, which is great. I have had problems disclosing some stuff, like some people just don't respond or aren't interested. And I have plenty more crashes still in the hopper. So, like I said, bugs aren't hard to come by in this space. And just to give you an example of the kind of bugs I'm talking about, this is in Expressif's Internet of Things platform built on top of FreeRTOS. And what they have is it's a client that runs and communicates with a cloud server. And what it will do is, send requests up to this cloud server that they control and process responses. So you can use their cloud server to manage devices like light bulbs and stuff like that. And if we look at this piece of code, is it possible to read it on the slide? Okay, good. Excellent. So if we look at this code, what it's doing is it's parsing a JSON response, and it basically takes, on line 321, it takes everything between the nonce, the JSON attribute name nonce, and the comma, trailing comma, and copies it into an 11-byte buffer on the stack. So this is a problem. So if we can impersonate the server or compromise it, then we can execute code on clients that talk to it. And as it turns out, due to other vulnerabilities, we can impersonate the server. So classic stack smashing bug. Similarly, for heap corruption, this platform has a web server that listens. And when it's parsing URLs for inbound requests, what it does is basically copies everything between the equal sign and HTTP in the URL, or in the first part of the request, into this PURL frame data structure that's allocated on the heap. So it's really easy to corrupt the heap here. This can only hold 40 bytes, but we can obviously send a lot more data here. So sending an oversized command is one example of how you can trigger heap corruption on this server. And you don't even have to have credentials or anything. You just have to send a request. So really, I mean, the 90s never ended. It's clear that these aren't deep bugs. They kind of just jump out at you when you look at the code. And in this space, memory corruption is really easy for developers to introduce. Developers that are, parsing requests and responses by hand, handling requests for constrained application protocol, multicast DNS, and so on. Requests that violate standard that don't meet the expectations of the developer can potentially trigger memory corruption issues. And vendors aren't always helping in this space. So, for example, I've seen SDKs that disable debugging assertions that actually perform a security function, or include outdated versions of libraries. So we want to understand, what's happening under the hood in the context of FreeRTOS when we're triggering one of these bugs, and really decide if these bugs are exploitable in the context of FreeRTOS. In order to put the bugs in context, we'll look more at the internals of FreeRTOS. So FreeRTOS, it's a real-time operating system. It's made by a company based out of the UK called Real-Time Engineers. It's been in development for over a decade, and it's a really lean OS. What it gives you is task creation, task being a process, and management, inter-process communication using queues, semaphores and mutexes for synchronization. It gives you a heap implementation or multiple heap implementations for memory management, and kind of in a broad stroke, that's really about it. It doesn't have things that you're used to in consumer operating systems like a notion of a user. It doesn't mandate the use of a particular TCP/IP implementation. You can use different implementations with it. So it's really glue for putting together a system. And as a result, it's quite tiny. I mean, it weighs in under 20,000 lines of C. You can port it to a new platform in under 1,000 lines of C in assembly. And in terms of the memory footprint, you can run it in under a K of memory. So this can run on really constrained platforms, which is great. And that's why I think it's been so successful and seen porting to so many platforms. Lightweight IP, it's a really popular embedded TCP/IP stack. It was originally written by Adam Dunkels, and this stack in particular supports a lot of different protocols, including SNMP, DNS, and so on. And it includes a lot of contributed servers, web servers, DNS servers, and so on. And you'll also find that a lot of commercial and hobbyist developers develop a lot of servers to take advantage of lightweight IP. So let's look at the data footprint of a task in the context of FreeRTOS. And can you read the? Yeah, it looks good. Okay, great. So if you look at this picture on the left here, we have the stack for a server task that's running on FreeRTOS. And on the right, there's the system heap. And all tasks, as well as the kernel, share a single heap in FreeRTOS. And there's also statically allocated buffer down in the bottom right. And if we look at the task stack, we see that it's growing downwards. The function that's currently executing is parse URL. And it was called by process request, so we know that this task it's reacting some data coming over the network. And there's a couple different kinds of data that it's using. The process request function has allocated 40 bytes on the heap, so we see this red chunk on the heap that's been allocated by that task. There's a pointer to this statically allocated buffer user agent, last user agent, and parse URL has allocated an array on the stack. And if we look over at the heap, we see that chunk that's been allocated has a header that includes a pointer to the next chunk, in this case is null, because it's been allocated. And also includes the size, which is 48 bytes, being 8 bytes for the header and then 40 bytes for the data that was allocated. And there's also an orange chunk, and this is memory that's been allocated by another task in the system. And we can see that the free chunks, they're arranged in a singly linked list. So the memory manager can find free memory when tasks request it. So we've already mentioned some of the key data structures here. We saw that tasks have a fixed stack region that's allocated actually on the system heap, which is interesting because it kind of combines the settings for stack and heap overflows in this context. Talking about the scheduler maintains multiple lists that it uses to decide what tasks to run. There's a ready list, a list of suspended tasks, a list of terminated tasks that need to be cleaned up. And when the scheduler is dealing with these tasks, it maintains metadata for an executing task in a task control block, or TCB. And when the scheduler is when a task is running, the scheduler will set a pointer to the TCB of the currently executing task, PX current TCB. We already saw that there's a single system heap that's shared by all tasks and the kernel. And lightweight IP also maintains its own heap, where it allocates memory for inbound packet data, data structures for tracking network connections, and so on. And there's also a system stack, and that's the stack that's used When the system initially boots, that's the stack that's where the main function's stack frame lives, for example, and that's also used by interrupt handlers. So we mentioned the scheduler, so let's talk a little bit about context switching. Real systems, they're always going to have multiple tasks. At the very least, we're going to have a server or network thread that's communicating with the network, and FreeRTOS always has an idle task that runs when no other tasks are able to execute. And scheduler handles context switching, and when it's switching context between tasks, what it will do is, first it takes all the register state for the executing task, including the program counter, and pushes it onto the stack for that task. And then it updates the TCB to keep track of, okay, where is the top of the stack for this task? Now, after I've pushed all the execution state onto it, and then it picks a task to run and kind of does the reverse process. It restores the state, including the program counter, off of that task stack, and then lets it run. So to see this visually, here again we have this example of a server task, and it's currently executing parse URL. And if we look over to the right, there's the TCB for this task, and we can quickly go through the entries in this TCB. So the first entry is tracking the top of the stack, and we see this is pointing actually into the middle of the stack for this task. And that's the value that was the top of the stack when the task was scheduled. So since then, the stack has grown. There's lists that the scheduler uses to, or entries that the scheduler uses to track information about the task in various lists, a priority, and there's px stack, which that's the beginning of this stack region of memory containing this task stack in memory, or you could think of it as the limit for the stack for this task. There's a pointer to a task name, a base priority that's also used for scheduling, and a runtime counter that's used for tracking performance statistics. So after context switching has happened, we see that we've pushed all the execution state of the task onto the stack. We updated the top of the stack, so the scheduler knows where this data lives. And the runtime counter has also changed. It's been updated because the task has executed for additional ticks. Talking about the heap in FreeRTOS, like I said, is shared by the whole system. We saw that free chunks are organized as a singly linked list. So it's less efficient to find free chunks, but it is more space efficient. And since FreeRTOS is targeting really constrained platforms, this is good. It's a win in terms of the memory footprint of the OS. Chunk headers contain a size and a pointer to the next chunk, and it uses first fit allocation strategy. So it'll walk through this linked list, find the first chunk that's big enough, set the next chunk pointer to null, and it also adds the unused part of that chunk back into the free list. So it'll write a new chunk header into the unused portion of that chunk and then put it into the list again so some other tasks can use it. And when memory is freed, for most of the implementations, the adjacent chunks are coalesced. So if you have two adjacent regions that are free, that becomes one chunk in this linked list. Lightweight IP supports multiple APIs for the programmer. There's a native API that you can use even if you don't have an OS. There's the netcon API, which is very commonly used, and then there's the familiar Berkeley socket API. And I mentioned netcon API because we'll talk about it more later. It's very commonly used and it's quite simple. The way it works is, it's event-driven. A client registers a handler that's called when, relevant events occur for a given socket. And in the case of UDP, the handler, the signature for the function looks like this. And if you look at the third argument, this pointer to pbuff, that actually allows the handler to access the payload for the inbound packet. So that's how we actually get data off of the network. As I mentioned, Lightweight IP uses its own memory manager, and that heap lives in a separate memory region. FreeRTOS has some features that when I first heard about them, I thought, okay, maybe this is some sort of exploit mitigation. One of the things it supports is stack overflow detection. So when I heard that, I thought, okay, some kind of canary implementation. It turns out it doesn't serve a security purpose. The system will halt if it detects stack overflow, and it's not meant to detect overflow of buffers that have been allocated on the stack. The way it works is If we look here, we have the stack region for a task. It's growing downwards, and the scheduler will perform up to 2 checks after a task has been suspended. It'll check if the stack pointer has gone beyond the beginning of that stack region in memory, the limit of the stack. And we can see that on the bottom. It's seeing if stack pointer points beyond that limit. And it also writes a kind of a canary value at the beginning of this memory region, and it will compare that to expected sequence of bytes to see if it was overwritten at some point, if the stack grew into this canary area while the task was executing. So we see if we were able to overflow a stack allocated buffer somewhere in the middle of this stack, we'd be writing towards high addresses, and neither of these checks would detect it. So it doesn't buy us anything in terms of security. I mentioned that FreeRTOS supports the MPU on the ARM Cortex-M3, and what this allows you to do is you can create restricted tasks and define memory regions up to 3, as well as the stack for that particular task. And the MPU ensures that the task can only write to those memory regions. The OS doesn't implement any controls that prevent restricted tasks from creating a regular task. So, restricted tasks, if you had code execution in a restricted task, you could escalate privileges by creating a fully privileged task and doing the rest of whatever you wanted to do at that point. So the MPU support, it's really intended to protect peripherals on the system, protect data on the system, and it's not really a security control. So we've seen some bugs, and now that you have some sense of the internals of the operating system, I'm sure a lot of you guys are already starting to connect the two. So now let's think like an attacker. We'll talk about vulnerabilities and specifically focus on stack buffer overflows because they tend to be common in the code bases that I've looked at. So when you're reviewing source code and you spot a potential bug, it's only the first step. At that point, you need to investigate. And in practice, that means deploying the software on real hardware, developing payloads, and seeing if you could trigger the vulnerability remotely. And in my case, I ended up accumulating a lot of hardware in the process. You can see some of it in the picture here, but I have more. And yeah, it's definitely a time-consuming part of the process. In terms of hardware that worked particularly well for me, the SAM4EEK, it's an evaluation board from Atmel with the SAMICE JTAG debugger, really worked well in the sense that I could build software using GCC. I could do debugging over JTAG using GDB, and I really didn't have any headaches in terms of debugging, so that was nice. And I didn't have to rely on Windows IDEs, for example, for building and doing debugging. On the ESP8266 side, the Olimex ESP8266 EVB board with the staggered J-Link pictured here allows you to do JTAG debugging, but I'll warn anyone who wants to do this that it's very painful. So you'll want to get a few in case you throw one against the wall. So stack overflows. In terms of stack overflows, now that we know a little bit more about the internals of the operating system, we know that when we're redirecting execution in the context of a stack overflow, that's happening in the context of a task. And we see on the right here, here's 2 function epilogues, and now we're controlling this return address, and we're able to redirect execution. With FreeRTOS, unlike simpler embedded systems, that task the task where we're exploiting the vulnerability has a dedicated stack. So that stack isn't being shared by interrupt handlers. So we have sort of an undisturbed space for exploitation. I wasn't sure if this was the case, but you're probably not surprised. The scheduler keeps everything running while our payload executes, so we don't have to mask interrupts or anything like that before we actually perform exploitation. And specifically on ARM, we can put the payload that we're executing anywhere. It could be on the task stack, but it can also be elsewhere in memory because the system is running with elevated privileges and everything is executable in this context. So the problem we're trying to solve, now that we have the ability to execute a payload, in practice that payload is going to be quite small. It's going to be subject to the limits of the particular vulnerability that we're looking at. And we want full remote code execution. We really want to demonstrate that this is a serious issue. So there's 2 general questions that we have to answer, or that one always has to answer in this context is, 1, where are we going to redirect execution? what code are we going to run? And with FreeRTOS in particular, we need to clean things up when we're done. We need to make sure that the task that's being exploited keeps functioning. And the reason is that task could, for example, could be the thread that handles network communication, for example. So if that task doesn't survive, then the system isn't accessible anymore. But in practice, neither of these things are that hard. So we'll talk about execution redirection first. And the simplest solution can often work. Task stacks in FreeRTOS are generally allocated when the system starts. And in that case, they'll be allocated at a known location. If you're creating tasks dynamically and it's being allocated on the heap, then you may not know where that stack region falls for the task. But that's much rarer. In practice, these tasks are generally created right when the system starts up. So we know exactly where the stack for a given task will fall in memory. And furthermore, if we're looking at a vulnerability, because these systems are simpler, we also know exactly where our inbound payload, where the data from the request that's actually triggering the vuln lives on that stack. So in that case, we know an exact address where we can go and execute code. If we're in a situation where we don't know exactly where the data lives on the stack, if we're looking at multiple firmware versions, or if there's multiple code paths that trigger the vulnerability, we still will have a window of addresses that's quite small, where we know the payload probably lives. So, if we need to fudge it 90s style with a ROP sled or something like a NOP sled, something like that, we have that option, assuming the architecture allows it. So this isn't true for all architectures. But ROP is a better approach in a lot of situations. In practice, if we have a register that references that inbound payload that triggered the vulnerability, then we can use ROP to manipulate the register, manipulate the address in the register, and then call it. So then we don't have to make assumptions or reason about where that payload lives in memory. It's just a side effect of the code that's running that it contains a reference to it in the register. And maybe it's a little funny to be mentioning ROP in this context because we're not trying to bypass a non-executable stack necessarily, but we use ROP because the gadget addresses are predictable in cases where the payload address may not be. And when we're using ROP, we can trampoline into our full payload that we can execute, and that payload could be on the stack or in the heap, or we can even use ROP. If we have enough gadgets, we can use a ROP chain to perform the exploit and not execute our payload. And we'll see an example of this in a little bit. FreeRTOS in particular gives us some other options, so we get some help from the operating system in this case. We have some platform-specific options. Code for FreeRTOS probably uses statically allocated data structures a little more commonly, so that gives us additional, predictable locations where we may be able to put data. And in some cases, we can even overflow them. So this is an overflow of ESP param, this statically allocated structure. And we see here we can overwrite min, wait, second, and upgrade timer. So we have this 36-byte window where we can put data. And overwriting them doesn't disrupt the system, and we can clean up when we're done. Also, a little bit troublingly, we can write right into the heap, but in practice, it's going to be hard to take advantage of that. But this is one of the other vulnerabilities that I disclosed. I'll also mention, we talked about lightweight IP having its own memory manager. If you look at driver implementations with FreeRTOS and lightweight IP, you'll see that ring buffers are used, and it'll allocate, when the system starts, a sequence of regions of memory for storing inbound frames. And this ring buffer also falls on a predictable sequence of addresses. It's driver specific, but you'll find if you look at how the driver is implemented, you'll find that these addresses tend to be predictable. So we can do kind of a variant of heap spraying where we just send lots of traffic to the device and fill this buffer and then jump to it. Kind of a Hail Mary option if nothing else is possible, and if other clients are communicating with the device, then this may not be successful all the time, but just mentioning it as an option when nothing else works. So we see that we really have a lot of possibilities. So if we're talking about a buffer overflow, I can't imagine a situation where you wouldn't be able to take advantage of it as an attacker. The other question we had is, what are we going to do when we're done? We don't want to break the target task. It could be lightweight IP's thread, and we need to be able to continue communicating with the device. And in practice, we're not only overwriting a return address, but we're blowing away registers that were preserved for the caller of the function that has the vulnerability. So you can spend a lot of time kind of piecing together not only a safe place to return when you're done with exploitation, but also safe values for those registers that you blew away. And because these systems are simpler, that's probably going to work out for you. But there is a better solution, and that is just to effectively restart the task. And in case of lightweight IP, if we're talking about lightweight IP with callbacks, you can restart the TCP IP thread, so return to the entry point for that task function. And this is using a reference to a statically allocated data structure, so it just keeps functioning. There's no disruption in network communications. This is going to leak memory. If intermediate functions allocated memory, you're not going to know where that is and not going to be able to free it. And you want to unroll the stack when you do this, as it would be unrolled when you first start the task, but this works in practice. And I'll briefly mention other bug classes. We already saw a static buffer overflow, and the impact, in that case, it's going to depend on what falls after that static buffer overflow. And we saw we could write into the heap, so while that's troubling in practice, when I looked at it, it really didn't look easy to take advantage of. So I have yet to find an interesting example, but we saw it's still a good place to put data for other purposes. The FreeRTOS heap, in terms of heap corruption, it's a really interesting topic, but in the interest of time, I can't talk about it. But if you're interested, definitely talk to me after the talk. And in my case, it's still an open problem. Someone may know more, but I haven't worked out all the details yet. So let's talk about exploitation. Let's look at an example end-to-end in this context. So in terms of our objectives, in this case, the example I chose, it's an overflow and a callback on FreeRTOS on an ARM Cortex-M4. And we're going to go from executing a small stager in the original request, or nearby, as we saw, we could always put it elsewhere in memory, to being able to execute arbitrary code on the system. And our goals here is not to destabilize the system. We want to keep the target service running. And we're going to use the facilities that the operating system provides to make this easy. So this allows us to not write a lot of code and achieve our objective. So to give you an outline of the approach, first we'll exploit the vulnerability to get code execution, and we're going to execute a staging payload. The staging payload writes a second stage payload somewhere to an unused area of memory where it won't be disturbed. Then we need to hook that payload into the operating system. So we'll add a network hook so the system runs the payload as a callback. And that callback, that lightweight IP callback, will then listen for inbound packets and execute them. And I wanted to illustrate this alternative for the particular bug I'm discussing. I mentioned it earlier, and that is in practice we often will have a register that references part of the inbound request that's triggering the vulnerability. In this case, if we look at R1, those first 4 bytes, it's a size, and then it's padded with FFFFFF. And the bytes that follow are actually part of the inbound request, and in this case, it's shellcode that we can execute. So instead of hard-coding the address of the payload and trying to reason about whether or not that's a reliable way to exploit this vulnerability, what we want to do is use ROP to branch to the address in that register. Unfortunately, on the ARM Cortex-M, you'll see that so we're adding 4 to walk past the size and these padding bytes, but we also have to add 1, and that's because on the ARM Cortex-M, the least significant bit of addresses that we synthesize in registers for branching always has to be set. And that's actually a really annoying aspect of the Cortex-M in particular because unlike the Cortex-A, where you can simply, you can find a gadget that branches directly to the stack pointer and run your code there, we first have to manipulate whatever register we're using. So it gets a little more complicated. So what we'll do is we're going to use ROP to do our arithmetic. and then branch. And for this particular vulnerability, it also turns out that I didn't have a lot of space to work with. I only had 48 bytes to build this chain, or 12 addresses. So it was a little constrained in terms of size. After we've exploited this rock chain and executed our payload, we'll restart the thread as we discussed. So just to go over this in a little more detail, as I said, we want to take R1, add 4 to it, and increment it, and then branch to it. And this system image, is around 10K, so it was kind of a question for me if there would be enough gadgets, but unsurprisingly, there are enough gadgets. But as always, the way we get there isn't always straightforward. So first of all, there wasn't a simple gadget just to move R1. So I want to take advantage of these arithmetic gadgets. If we look in the last 4 gadgets that we're using here, that are adding 4 to R2 and then incrementing R0, which contains the same value as R2. I wanted to take advantage of those, and those were some of the few gadgets that I found that would actually perform the arithmetic. So the first step was moving R1 into R2, these first 3 gadgets, and that actually required pushing data onto the stack and then popping it to swap the registers, or to move the registers, I should say. So once the register has been moved into R2, things get simpler, and we can use the gadget in the second section to add 4 to it. We then increment it, and then we're able to branch to it. And once we've branched into our payload, then we perform the rest of the exploitation. So this solves the first problem in sort of a general way, in that we're able to execute our stager. But we need to write the code for our callback that's also part of our request, somewhere in memory where it's not going to be disturbed. And we can use memcopy to do this, so the OS gives us a function that makes it easy. And there's more than one place where you can put it. My choice was to put it past the end of the system stack buffer, so this is unused real memory where nothing will touch it. We could allocate memory in the heap and store it there, and also it wouldn't be disturbed. We could use lightweight IPs heap as well, allocate some memory there, and we'd know that it wouldn't be disturbed. And we could even put it in the stack of the exploited task. So that's the beginning of the stack in memory, that limit, PX stack. If we know that that task doesn't get close to that limit, then we also have some space where we could put it. And that might be more useful in cases where you're using the MPU, and you can write to your own stack if you needed some place to put it. I should mention on the LX106, the core on the ESP8266, we have fewer options. That core requires code that's being executed needs to be put in a specific region of memory called instruction RAM. So in that case, we'd need to put this payload there and use ROP before we can hook it into the operating system. So once we've written the payload somewhere in memory, we need to wire it in, and callbacks are the simplest way to do this. And it's ideal because we're not going to interfere with scheduling of any tasks. We're not going to starve other tasks in the system, or we don't need to think about the problem of starvation. So it makes it really simple. In the case of UDP, it's really only 3 calls. So we create a protocol control block for UDP. We bind it, in this case, to port 53 in the second call. And the third call is really what wires in this callback. We call UDP receive, and this is telling lightweight IP when we have inbound data on port 53, call the function at this address, call at payload, and that's going to call our callback. So this allows us to run payloads when we send UDP traffic to 53 on the device. And you could also do this as an outgoing connection. I just chose this particular example because it fits on a single slide. But we do have alternatives because callbacks aren't always supported. It depends on how the firmware for the system has been built. So if callbacks aren't an option, we can create a whole new task. And once again, the operating system makes that simple, so we can call xtask create. And in that case, our payload would have to do a little more work to set up a listening socket or make an outgoing connection. But at that point, we have a task that's scheduled and run that actually executes the code that we want it to. In this case, starvation is a consideration. The scheduler is always going to run the next available task that has the highest priority. So we need to consider starvation, and in practice that means making the task block for a while. I say a while because you need to pick a value that works for the particular system that you're looking at. But yeah, conceptually this isn't too different from the callback example, but we're using like a full task instead of just a callback. So what does a callback do? What it's going to do is listen for inbound packets and execute them. So we have sort of RCE on demand, and we've gone from executing something small that wires it in to being able to execute whatever shellcode we can fit in a packet. We don't want to run just any traffic that hits the device, so we need to mark our packets in some way. And a simple way to do this is just mark the packet with some magic value that indicates to the callback that it's going to be safe to run. When the callback sees a packet that has this magic value at the beginning, then it goes ahead and branches to it. And again, on the LX106, because we can only execute code in a certain region of memory, we have to actually first copy the packet into IRAM and then execute it. We can implement more complicated logic if we need to in the code that we send in the packet. So if we needed sequence numbers or something that gives us at most once execution, maybe it could update the magic value and require that new value be sent with subsequent packets. So this is going to allow us to execute larger payloads reliably. And the implementation can be quite small. So here's a 12 instruction implementation for ARM, just to give you an example. And I pulled this off of my system so we can see that this is written past the stack, system stack boundary, which is 2001, 0130. So the first thing we have is our magic value, dead beef. And if we put that into an inbound packet, then this callback will actually run the packet. And the first two instructions, the first thing it does is preserve R3 and store the return address. And then we access R2, that third parameter, which is a pointer to the pbuf containing our packet data. We access the payload pointer there to actually access the payload of the packet. And the next 5 instructions, this is where the logic of the callback is really happening. So the first thing we do is read the magic value from the beginning of this memory region. So we're reading from 2001, 0130, dead beef, and storing that in R1. We then read the magic value out of the packet. We read those first 4 bytes. And we also increment R0 by 5, so we're ready to branch to it if the magic value matches. The third instruction there is doing a comparison to see if those magic values match. If they don't match, then it's going to go ahead and clean up. Otherwise, we see this BLX to R0. That's going to actually execute the packet. And then there's cleanup. There's 5 instructions at the end that actually perform the cleanup. So we get back our pointer to P. We construct the address of pbuf free in R1, and we have to do that in 2 instructions because it's too big to do in a single instruction. And then we actually call free, so we're being good citizens here and not wasting memory. And once we're done freeing the packet, then we return. So we tell Lightweight IP that we're done handling this inbound packet. And we can go on our merry way. So what can we do with this? This is going to live in system memory, so it won't stick around after the device resets. But we can write to flash to make it permanent. But the fact that it's gone on reset, it's kind of troubling in its own way because there wouldn't be any evidence of compromise after the device was reset. We can send traffic off of secondary interface as one example. We can access peripherals on the device. And in the interest of time, although I'm running a little bit ahead of time, I didn't plan to do a demo during the talk, but definitely just ask me for a demo. I'd be happy to give you a demo after the talk. So let's talk about conclusions. In terms of recommendations, and it's hard not to be a little pessimistic here. In 2016, here we are telling developers that they need to manage memory safely in C. And like I said, there's an astonishing amount of code being written for FreeRTOS, one platform, but at least half a dozen other platforms have developers actively writing new code in C. So we're looking at many more years of memory corruption for these softer devices. And because these devices are softer, it's important to isolate them. You don't want to have them coexisting with more sensitive systems. You want to put them on their own part of the network and isolate them. As security professionals, we need to raise awareness, make sure that people understand the consequences of bugs like these. In this case, they're catastrophic. We need to audit this technology and help people fix vulnerabilities, report them, and see to it that they get fixed. And there's an opportunity here, I think, for vendors to implement additional protections for these embedded operating systems. With FreeRTOS, we saw like having canaries, heap pointer integrity checks, taking advantage of non-executable memory for platforms that support it, and randomizing the layout of memory. These would all be fantastic things that would make an attacker's job harder. And the operating system is open source, so any one of us could do this if we wanted to. So briefly to go over conclusions. Whoops, went the wrong way, sorry. Future work, I mentioned FreeRTOS is one platform. If you're not interested in FreeRTOS, there's easily a dozen other platforms out there, more TCP/IP implementations, and plenty more to look at for anyone who's interested. So I encourage people just to see what's out there and try to find bugs. I've only scratched the surface of the auditing that I've done so far, so I'm going to keep looking for vulnerabilities. The LX106 and the ESP8266, I hinted at it briefly in the talk. There's additional challenges when it comes to exploitation there, and that's something that I'll be focusing on in the near future. The FreeRTOS heap is really interesting, and I'm planning a white paper, so follow me on Twitter and look out for more details there, and talk to me after the talk if you're curious. A couple of people to thank. Siavash from NCC Group, he suggested RTOSes as a research area and kind of got me interested in this research. Stephen Ridley and Stephen Lawler have an excellent ARM exploitation training, so if you found that part of the talk interesting, definitely encourage you to check out that training. All the reference research has been a huge help, and definitely anyone I forgot, thank you. And folks who reviewed the talk with me and gave me feedback. ShmooCon organizers for putting the event together, and most of all, thanks everyone for coming. And that's it, and we actually have a few minutes for questions, which I'm relieved. So if anyone has any questions, fire away. Yeah. That was an ARM example, so in that case, we don't need to store it in our IRAM. It's living in lightweight IP's heap, and we can execute code that's on lightweight IP's heap, so it makes it simpler. We don't have to copy it before we're executing it. Yeah, on the LX106, you would first have to copy it before you actually jump to it. So you would check that magic value. If it matches, copy it over and execute there. Yeah. Uh-huh. It's hard. So you can run FreeRTOS in QEMU. So it would be emulating an ARM platform. So that's handy. But in terms of the fuzzing, that's one hurdle that you're going to hit, is that if you're looking at software for MIPS or for the ESP8266, there really isn't, well, maybe in MIPS there is an alternative, but for the ESP8266, there's no alternative to real hardware. And the other thing is that because it's sensitive to memory layout and so on, you may do your investigation in an emulated environment and then find that the details are different on a real platform. So there's a trade-off there. But yeah, QEMU would be the way to go for ARM, definitely. Any other questions? All right, thanks, guys. And definitely hit me up if you want a demo.